Hey there, and welcome to a short video about how to compute the derivative of composite functions with two or more arguments. My name's Frank, and I will show you a little bit trick which helps you to apply the chain rule to solve this problem. So consider you have a function of two arguments and call it f. And we have two functions g and h which will play the role of our inner functions. And the question is how to compute the total derivative of this composition. So we have f. And in the first argument, we plug in the function g evaluated at x, and in the second argument, we plug in the function h evaluated at x. And the question is, what's the derivative of this composition? So you can see the answer here. Well, you have the derivative of f with respect to the first argument multiplied with g prime. And you have the derivative of f with respect to the second argument multiplied by h prime. The question is, how do we get there? And I will show you a little trick which maybe helps you to solve other problems. So before I show you this trick, let's start with some definitions. So we say a function which goes from the space Rn to the space Rm is said to be totally differentiable at a point A if there exists a linear mapping L such that this limit goes to 0. I'm pretty sure you've seen this thing before if you've heard analysis 1 or at least analysis 2. You know that the derivative is all about linear approximation, and the linear mapping L is just the approximation. And so a shorthand notation for this linear mapping is just f prime evaluated at a, and f prime is called the derivative of f. If we know a little bit more about our function f, in fact, we know it must be totally differentiable and in such a way that all partial derivatives exist, then we can express its derivative as this super nice matrix. And this matrix is called the Jacobian matrix. It's a very common matrix, but we do here a little bit change of notation, and I want to point it out because we are identifying the linear mapping f prime of a with its matrix representation. So if you go back a little bit, this L here, which is f prime of a, is a linear mapping between the spaces Rn to Rm. But here it's just a matrix. The thing is, if you have a mapping between between finite dimensional spaces, so Rn to Rm, both are finite dimensional, we can identify it with its matrix. This is quite standard. And on the other hand, every matrix will give you a linear mapping. So between finite dimensional spaces, linear mappings and matrices are basically the same. So just keep this in mind. This will give you a matrix, but it's the representation of a linear mapping. So I told you that we will use the chain rule. So here you have the chain rule. We have g. It should be differentiable in a point A, and f should be differentiable in point B, which is just g applied to A. And we know that the composition, so f circ g, is differentiable in the point A, and we have this nice formula. So the composition, the derivative of the composition applied at A is just f prime evaluated at g applied to A times the derivative of g at the point A. And we will use this theorem to actually compute the total derivative of our initial problem. So, but how do we use it? Here again you can see the problem. We have the composition, so we call it L. It's f applied to g applied to h. And well, first of all, we do a little bit change of notation. We know that the space R times R is basically isomorphic to the space R2. So we can write in this way. So the f applied to x applied to y is just f applied to the vector x and y. So it's just a change of notation, but this will fit into our general framework. So that's why I've done it. The derivative of f, well, just write it down. We have a vector which is in the space R1 times 2. And here's the first derivative, here's the second derivative. And keep in mind that z is now a vector in the space R2. This will be important later on. And now here comes the trick which will make us life much more easier. We introduce the mapping, we call it I. I maps just the real number x to the vector g applied to x and h applied to x. And its derivative, well, it's just the Jacobian matrix here, just g prime of x in the first argument and h prime in the second argument. So nothing special here. But now we combine everything. So L of x is just f applied to g to x applied to h of x, but with our isomorphic spaces, we can just apply f applied to the vector g and h. So nothing special here. But this inner vector is just I of x. Well, just by definition. But if you look at this is just the composition. So this expression here is just f circ I applied to x. Well, and now you can see what happens. Now we apply the chain rule. So just apply the chain rule. So derivative of the composition here is just f prime applied to I times the derivative of I. I of x, well, derivative of f applied to I to x is just this expression here multiplied by this vector. Well, this is just an easy vector times vector multiplication, and you end up with the expression that I showed you in the very first beginning. So the trick here was, so it's nothing special here, but the trick is to introduce this mapping I, which makes life much more easier. And well, you can use this in several forms, and it's a quite helpful trick. I've used this several times to make things more easier. And well, that's basically it. I hope you enjoyed this short video, and this trick may help you to solve your derivative problems using the chain rule. So have fun, see you around, and have a good time.